Okay, we're continuing to solve more improper integrals. In the previous video, we worked a bunch of type 1 improper integrals. That's where you have one of the limits of integration going off to infinity or negative infinity, or you could potentially have both, the integral from negative infinity to infinity. And so in this video, we're going to work some of the type 2 improper integrals, where the limits of integration, within the limits of integration, is an infinite discontinuity. Now, one thing I didn't mention in the previous video that I should have mentioned is that it's not like when you have an integral that it's either going to be type 1 or type 2. When you have an improper integral, either type 1 or type 2, you could have both. And so for each of the problems that we worked in the previous video, what I should have been saying was that for every problem, for any definite integral, you're going to, no matter what the definite integral is, you're always going to check that over the limits of integration, is the function, does it have any discontinuities? Right? If it has a discontinuity, then you're going to need to stop and take a step back and analyze the problem. And really, the improper integrals, when it comes to discontinuities, it's mainly about infinite discontinuities. But from a math standpoint, like we talked about in the textbook section, really an improper integral, the type 2, is for any discontinuity. So if you have a definite integral and you look at the limits of integration, and the limits of integration could be two finite numbers, or it could be have infinity, negative infinity or infinity, and you realize that within the limits of integration, the function has a discontinuity, one or more, then you're going to apply, from a technical math standpoint, you're going to treat it, even if you have a discontinuity that's not an infinite discontinuity, but like a jump discontinuity or removable, you're still going to then treat it as a type 2 improper integral. And I talked specifically about why this is when we went through the textbook. Okay, so again, I should have been approaching every single problem from the beginning, starting from the beginning of the previous video this way, but the first thing we do is we look at any definite integral, no matter, even if it's improper or not improper. Well, even if the limits of integration don't contain an infinity, you look and you say, okay, within the limits of integration, here it's from 0 to infinity, do we have a discontinuity? Okay, well, this is 1 over e to the root y. Okay, when y is equal to 0, e to the 0 is 1. So we're starting at 1. Then as you go to infinity, you can plug in any number greater than 0 here, and there's no issue. So this is fully continuous over from 0 to infinity. E to the minus square root of y is continuous. Okay, so with that, we know that we have strictly a improper integral, a type 1 improper integral. That's it. Okay, so this is the limit as t approaches infinity of 0 to t. All right, so let's come off to the side and solve this. So we're going to say that we're going to do a simplifying substitution. We're going to say that u is equal to the square root of y, so u squared is equal to y. Therefore, 2u du dy is equal to 1. So 2u du is equal to dy. All right. So when y is equal to 0, u is equal to 0. When y is equal to t, u is equal to root t. And we've got e to the minus u with the u. Okay, so we can do integration by parts now. We can say that, all right, so we've got okay, so we're going to say that z is equal to u dp p is equal to e to the minus u du. So you've got minus e to the minus u, and then dz is du. So, all right. Z times p, but let's include the 2 here. So minus 2u e to the minus u evaluated from 0 to root t minus p, the integral of p dz. So plus, and we bring the 2, integral from 0 to root t. Okay, so this is going to be minus 2 e to the minus u evaluated from 0 to root t. Okay, so we've got minus 2 root t e to the minus root t, and then plugging in 0, that goes to 0, minus 2, and then e to the minus root t minus 1. So minus 2 root t okay, there we go. So this is equal to, we can take out a 2, and we've got root t e okay. As t approaches infinity, you have e to the minus infinity, that goes to 0. This goes to 0, so you're just left with, oh no, there's not a 2 here, this is a 1. So this goes to 1 as t goes to infinity. 1 times 2 is 2. So this converges to 2. Okay, so here we go. We're integrating from 0 to 1, but 1 divided by 0 is a discontinuity, an infinite discontinuity. And so you might say, well, okay, so what? This is like at the boundary. Why don't we just do the integral of 1 over x is natural log of the absolute value of x. So natural log of 1 minus natural log of 0. What's natural log of 0? So you can't solve it that way. Right, because this discontinuity isn't in the middle of the limits of integration; it's at the end, but still. Okay, so how do we deal with type 2 improper integrals? And this is just type 2 because we're not going to infinity or negative infinity. Well, okay, if the discontinuity is in the middle of the limits of integration, then we're going to have to break it up into 2 separate integrals. Here, it's just at the end, so we're just going to have to do 1 integral. And what we do is this. It's very similar to the type 1. We're going to say the limit as t approaches, and this is going to be a t here, and we want that to approach 0 from the right, okay, of what? You see, that's how you do it, because you can imagine we're integrating from a lower limit to 1, but we want that lower limit to we want to push that lower limit as close as possible to the discontinuity in the corresponding direction. In this case, it's from the right. It's coming from the top. You could say. All right, what is this? So we've got minus natural log of the absolute value of t. Okay, so we've got the limit as t approaches 0 from the right. Take out the minus. Okay, well, t is always positive coming from the right of 0, so we could just make this t. And this is equal to negative infinity, but with the negative out front, this is positive infinity. So this diverges to positive infinity. Okay, so at minus 2, you're dividing by 0. And then everywhere else between minus 2 and 14, it's continuous. So we want to say the limit as t approaches minus 2 from the right Okay, so let's evaluate this integral, and I'm going to go ahead and just get the indefinite integral first. So we've got this radical here. Let's go ahead and substitute for the entire radical. So u to the fourth is equal to x plus 2 4u cubed du dx is equal to 1 4u cubed du is equal to dx. So we've got 1 over u, and then take out a 4u cubed du, u squared du, so we've got 4 times 1/3 u cubed. 4/3 times, okay, we would do x plus 2 to the 3/4. Okay, so now, okay, 4/3 x plus 2 to the 3/4, and then we want to evaluate this from t to 14. All right, so 4/3, let's take out the 4/3. We've got 16 to the 3/4 plus t plus 2 to the 3/4. Cube root is, or the fourth root of 16 is 2. 2 cubed is 8. So 4/3 times 8, that's 32 over 3, plus 4/3. All right, so we've got the limit as t approaches minus 2 from the right of 32 over 3 plus 4/3. Okay, so what does t plus 2 to the 3/4 approach? As t approaches minus 2 from the right, it's 0 to the 3/4. So this approaches 0. So 32/3 is what this entire limit approaches. This is equal to 32/3. Okay. So we're going to be passing over 0. Minus 2 to 3, we're going to be passing over 0. So now we have the discontinuity is in the middle here. So of the limits of integration. So what do we do? Well, we just do two separate integrals. We're going to say we have the limit as t approaches. So we're going from minus 2 to 0. So we're saying, in this case, 0 from the left. You see? Because we're approaching 0 from the left. We're going from minus 2 to 0 of you see? Exact same concept as what we did for the previous two problems, except now we're approaching the upper limit. The discontinuity is at the upper limit. Okay, but plus the limit as t approaches 0 from now the right of the integral from t to 3. Okay, so, all right, what is... This is x to the minus 3 over minus 3. So the integral of x to the minus fourth is x to the minus 3 over minus 3. So minus 1/3, and then minus 1/3, then so minus 1/3, then minus 1 over minus 2 cubed, so it's going to be like that. Okay, now this is the same idea, but now we're doing like that. So, okay. Take out a minus 1/3. You've got, okay, take out a minus 1/3 again. And okay. So as t approaches 0 from the left, this is going to negative infinity. All right, so, and so we've got negative infinity times minus 1/3, that's positive infinity. Positive infinity minus 1/3, so this goes to infinity. And then this is going to infinity. So you've got, yeah, this is just going to diverge. Okay, so we've got 1 over t cubed as t approaches 0 from the left. You're cubing a small negative number, so this goes to negative infinity. Minus 1/3 times minus infinity is positive infinity. Minus 1/3 times 1/8 is positive infinity. Okay, so here let's put the minus sign out front and look at this, and with not considering the minus sign. So we've got 1 over 3 times 27, positive number, minus 1 over, so 0 from the right. This is going to be positive infinity. So 1 over 3 times 27 minus positive infinity is minus infinity. So you end up getting infinity plus infinity, which is infinity. This diverges to infinity. Okay, at x is equal to 1, we're dividing by 0. So we want to say, split this up into two separate integrals. The limit as t approaches 1 from the left, and going from 0 to t. Okay, then the limit as t approaches 1 from the right. Okay, so the integral of just the indefinite integral, we could make a u substitution here, but if we just integrate, so all right, what is the integral of x to the minus 1/3? That's going to be x to the minus 1/3 plus 1 is x to the 2/3 over 2/3, so 3/2. And so that means that this is going to be 3/2. Okay, so evaluating this from t to 0, you've got t minus 1 to the 2/3, and then minus 1 to the 2/3. So the cube root of minus 1 is minus 1. Minus 1 squared is 1. So, okay, now evaluating this from t to 9. So, okay, cube root of 8 is 2. 2 squared is 4. And then, so 6 minus, okay, so we've got, and then here, all right, as t approaches 1 from the right, this goes to 0. We're left with minus 1. So we got minus 3 halves here. As t approaches 1, this goes to 0. We're left with 6. So minus 3 halves plus 6. Minus 3 halves plus 9 halves. Okay, so tangent theta has a discontinuity, a vertical asymptote at pi over 2. So we're going to say the limit as t approaches pi over 2 from the left Okay, now what is this integral? We want to write this as secant squared theta minus 1. So then we've got so this is tangent theta from 0 to t, because the derivative of tangent theta is secant squared theta, minus theta evaluated from 0 to t. So this is tangent of t minus t. Okay, so what we've got is the limit as t approaches pi over 2 from the left of tangent of t minus t. And so this should be positive infinity as tangent of t approaching pi over 2 from the left. Let's make sure. Yeah, infinity minus pi over 2. So this is just infinity. This is divergent, diverges to infinity. Okay, so the issue here is the 0, because natural log of 0 is undefined. So we want to say the limit as t approaches 0 from the right Okay, so what is this integral? Integration by parts, we'll say that u is equal to r, so du is dr. Or no. We're going to say that u is equal to a natural log of r, so du is 1 over r dr. dv is equal to r dr, so v is 1/2 r squared. So we've got u times v evaluated from minus the integral of v du. Okay, so natural log of 1 is 0, so we just plug in okay, now integral of r is 1/2 r squared, so okay. So we've got the limit as t approaches 0 from the right of okay, as t approaches 0 from the right, natural log of t approaches negative infinity, t squared approaches 0. So we this is indeterminate here, and then this goes to 1/4, and then this goes to 0. So we need to, we've got an indeterminate form here of type 0 times infinity. So what we can do is say, all right, so the limit, let's bring out this 1/2. We want to write this as a quotient. So let's do this. Okay, approaching 0 from the right. This goes to negative infinity. This goes to positive infinity. So infinity over infinity, L'Hopital's rule. Okay. You've got 1 over t, and then so t to the minus 2, the derivative, minus 2t to the minus 3. So minus 2 over t cubed. All right, 1 over t times t cubed over minus 2. So minus 1/2 t squared. So we can take out the minus 1/2. And this limit is equal to 0. So this goes to 0, this goes to 0. We're left with minus 1/4. So this converges to minus 1/4. Okay, so minus 1 to 0, but we can't divide by 0. So we're going to, now this is not, we just need to do one limit because the 0 is not in the middle of, in the middle. So we would have the limit as t approaches 0 from the left, minus 1 to t there we go. So okay, we can, let's solve this. We can say that u is equal to 1 over x. Therefore, du is minus 1 over x squared dx. And so what we've got is when x is equal to minus 1, u is equal to minus 1. When x is equal to t, u is equal to 1 over t. Okay, now we've got e to the 1 over x is e to the u. Then we've got 1 over x squared dx is minus du. And now we're just left with a 1 over x, which is u. So we've got u e to the u du. Okay, integration by parts. We say that z is equal to u, dp is equal to e to the u du, dz is du, p is e to the u. So this is equal to minus u e to the u evaluated from minus 1 to 1 over t minus the integral of p dz, but then we distribute this minus, so we're going to get plus the integral from minus 1 to 1 over t e to the u du. So we've got minus 1 over t e to the 1 over t minus, then minus 1 is just 1, e to the minus 1, so 1 over e, so this is just going to be minus 1 over e, okay, plus, okay, so we've got e to the 1 over t minus 1 over e. Okay, so we've got the limit as t approaches 0 from the left of, so e to the 1 over t minus 1 over t e to the 1 over t minus 2 over e. All right, so approaching 0 from the left, 1 over to a tiny negative number is a large negative number, so this is going to 0. This is going to 0. This is going to negative infinity, so we're going to need to analyze that further. Okay, so, and then this is just a constant, so okay, so what is the limit as t approaches 0 from the left of 1 over t e to the 1 over t? So we want to write this as a ratio, and now we can see that this is approaching 0 in the numerator and 0 in the denominator. So with L'Hopital's rule, we end up with, this actually isn't going to work out too well. We're going to end up with e minus e to the 1 over t over t squared. So let's try this. Let's try 1 over t over 1 over, that would be e to the minus 1 over t. Okay, you plug in 0. This goes to like infinity or negative. This goes to negative infinity, and then this goes to e to the 1 over, this is going to be e to the positive infinity. So it's infinity over infinity, some sort of infinity over infinity. So we've got minus 1 over t squared, and then e to the minus 1 over t times the derivative of minus 1 over t. So 1 over t squared e to the minus 1 over t. Right? You see how that works? The derivative of e to the minus 1 over t is e to the minus 1 over t times the derivative of minus 1 over t, which is minus 1 over t, which is 1 over t squared. So minus e Okay. As t approaches 0 from the left, this goes to negative infinity. So 1 over e to the infinity approaches 0. So this approaches 0. This approaches 0. So this approaches minus 2 over e.